Which PNT satellite constellation is your favourite?
Galileo, you know why?
Yeah, why?
Because I was one of the originators of the system.
Oh, so it's your baby.
So the joke always is that when you're in an aircraft which is using these systems and you get to where you're going, take a penny and put it in Washington's account. and if you don't get there, say good words to the maker.
Welcome back to the Zero Pressure podcast series, a relaxed conversation with those on the cutting edge of science and technology. Hosted by me, Helen Sharman, and presented by Imperial College London and Saab. The Zero Pressure podcast is looking at how science and technology positively can contribute to solving complex, interrelated global challenges of today and tomorrow. This time we're talking about positioning, navigation and timing, PNT services, their use within many aspects of critical national infrastructure and their extensive impact on our daily lives, be it farming or finance, healthcare or navigation, commercial or defence. I'm very pleased to be joined on Zero Pressure by our guest, Professor Washington Ochieng, Head of the Department of Civil and Environmental Engineering and Chair in Positioning and Navigation Systems at Imperial College London, where he's also Senior Security Science Fellow at the Institute for Security Science and Technology. Washington spent a few years working on satellites in industry before joining Imperial. He's interested particularly in intelligent traffic control for security and to regulate traffic in congested streets and railways, as well as in air and marine traffic management. Amongst his other roles, Washington advises the UK and Kenyan governments and the European Parliament on matters including science policy, infrastructure and critical dependencies. Washington, welcome to Zero Pressure. Thank you for joining us today.
Thank you very much, Helen. I have been a long-time fan and I'm delighted finally to be here talking to you.
Let's start with some real meaty stuff. I mean, can you explain what positioning, navigation and timing actually means? How do these things work?
Okay, so the first thing is that positioning, navigation and timing underpins life as we know it. And I'll explain why in a minute. So position in general is a geometric in the sense that systems that give you your positioning information, they give you what we call coordinates. So people know about latitude, longitude, and so on. So that's what you get. And it is until you take the figures, the numbers in terms of latitude, longitude, and you place them on a map that you now get what we call location. So I just want our listeners to be clear that position itself is are numbers, and then when you take those numbers and you lay them on a map, you get your location. The other dimension to this is time. So timing is obviously important, as we know. Everybody has a watch, or most people have. So it's not really about the fact that humans want time, but usually what happens is the quality of the timing information and for what application in general. So that's where we go. Now, once you have your position and you have your time, we then have what we call derivatives. So, for example, if you change your position, you know how the distance that you've actually traveled and direction. So you can always determine the next point you're going to go to. But if you bring in timing, then you can do things like velocity. So you can think about calculating your speed, velocity, and so on. And if you have all of that information, then you can start to navigate. So you can actually move from A to B, controlling not only for your displacement, speed, and so on, but direction as well. And actually knowing where to go with the use of a map. So this is where navigation comes in. So position and time needed to derive other things that enable you to navigate, i.e. move from A to B.
So how do we actually get these services to work? We use satellites, right, to enable us to position, navigate and time our way through life. How does the technology work?
Yeah, so there are two things you need to measure. Two things only, which is very interesting. The first is distance. Yeah, and the second is angle. And you can use distances only, angles only, or a combination of distances and angles to position yourself. It's very, very interesting. And anything that we develop, any technology, however clever, they'll be giving you one of both of those things. So what you have is basically beacons whose positions are known, call them satellites, 23,000 kilometers from here, and they transmit signals that our receivers here obviously receive, And all our receivers do is to compute the time of travel of the signal from the satellite to the receiver, and you multiply that by the speed of light in vacuum, 3 times 10 power 8 meters per second, and that is the distance between yourself and the satellite. So what you need is an additional 3 or more satellites to be able to calculate your position in the X dimension, in the Y dimension, Z, and of course, time. So those are 4 things you need to get, and you need at least 4 beacons, i.e. satellites, to be able to calculate that, knowing where the satellites are. So the actual calculation is pretty simple. The actual concept is as simple as I've described it. So I hear you asking, where is the challenge? The challenge is mainly in making sure that the distance you compute is as error-free as possible. Why? One of the main reasons is that we have just used the speed of light in a vacuum, and not the entire distance between us and satellites is not vacuum. So some of it is, and some of it is affected by the atmosphere. So we need to really do the research to make sure that we can remove all the interferences that actually occur in terms of the error types between us and the satellite. So a lot of research has been going into computing those distances and or angles to be of the highest precision and accuracy to enable us to deliver the best position and time information.
How could our reliance on PNT services make us vulnerable? I mean, GNSS, Global Navigation Satellite Systems, it's not just used to get me from where I am now to where I want to be, is it?
Yes. So one good example is a country's critical national infrastructure. So I was involved in a study recently by the UK government on its critical national infrastructure and our dependency on PNT and in particular GNSS. And just to give you an example, the communication sector, telephony and so on, obviously the synchronization of the network is required to a very, very high precision in terms of time to deliver communication across the world, actually. And the systems that we use obviously have been depending on atomic clocks, which are obviously quite expensive to have huge networks of these things. I mean, there's also been development of fiber networks and so on. But GNSS, as I said earlier, 40 nanoseconds is the basic accuracy you get. You can get a lot more with that if you're using more sophisticated processing platforms and models.
So why do we want more?
Yeah, because synchronizing. The other example is trading. Okay, so if you can imagine trading between New York and London, and the timing precision required related to the amount of money that you could lose, we are looking for very, very high precision and very high accuracy clocks and very high integrity clocks. Otherwise, you're going to lose a lot of money. If you take the transport sector, even in London buses, to be able to calculate the times that buses arrive and buses travel at bus stations and travel to the next one, that requires very good positioning accuracy. And that needs to be accurate, has integrity, continuity, and availability. So these systems, PNT and GNSS in particular, underpin critical national infrastructure, let alone the masses. Everybody has GPS, GNSS in their phones, and they're all using sat-nav functions, right? So it's ubiquitous. It's something that's needed, and it's needed in much more higher levels of performance, depending on the accuracy as we want to improve the efficiency and standard of living. That's what happens.
Yeah, there's the electric grid as well, as I understand it, isn't it?
Yes, and the grid requires both positioning and also timing in terms of how we manage energy distribution and so on. So, this is why countries like the United States and so on were building this great utility at a significant cost, as a basic government-provided service, because it underpins what you might call the duty of a government in terms of providing safety and security for its people. But it's not just about security in terms of defense. It's security of food, security of energy. And PNT is fundamental to that. So in relation to vulnerability, what we were looking for is that if it's that important, then we must make sure that we understand its vulnerabilities and that we put in place mitigations or interventions to ensure that we don't lose it. A recent study by a company called London Economics showed that the UK would lose more than £5 billion, right, if you monetize it for a 5-day outage of GNSS.
Well, £1 billion every day we would lose, and that's
and this is it's they say minimum, and I don't think that number comes close, by the way.
Oh, and think worldwide then, if you multiply
to what
that up.
it would be. In addition to the London economic study, an RTI international study commissioned by the US's National Institute of Standards and Technology, NIST, which was released in 2019, estimates that GPS generated roughly $1.4 trillion in economic benefits just in the US alone, since the system was available for civilian and commercial use in the 1980s. Governments obviously must be thinking, or service providers must be thinking, how do we ensure that we do not lose such a fundamental utility?
What might make us lose this if a satellite were to stop working for whatever reason? Presumably there's the redundancy in the number of satellites in these constellations, but let's say a significant enough number of them stopped working, we would lose the whole ability to do everything that you just mentioned.
Yeah, and this is the problem, isn't it? And actually, for many years, we didn't have, evidence of these systems failing. We do now. We had more than a day's outage of the entire Galileo constellation because the clock facility in Italy failed. I mean, that was probably the first time ever that a whole constellation failed. And what that actually means, however good they are, they fail, right? And so because of that, and because of the role they're playing, given what we just discussed a few minutes ago, we must make sure that we understand the vulnerabilities, and we then must make sure that we address the vulnerabilities so that this critical utility is available. The level of protection that's required isn't actually there. So I've referred to this sometimes as we are using it anyway. It's not protected in the right way. It's like sleepwalking into the abyss, which is quite a statement to me.
It is, isn't it? Whoa. And satellites, technology just sometimes doesn't work for all sorts of reasons, but we also have to occasionally to be concerned that some of the operators of the satellites might not want them to be used by other countries, let's say, for certain purposes. Have there ever been times when satellite systems have been turned off?
This is called denial of service, which is a threat. It is a threat. We actually haven't experienced a case, apart from the Galileo situation, when the constellation actually failed due to this clock facility, and that was unplanned. But denial of service by the owners of systems is obviously there. And the reason for that is that there's a huge advantage that you get by having global positioning and navigation systems. There's a huge advantage, particularly in terms of war and things like that, right? And so they have the right to deny you a service. That's why ownership of, let's say, a GNSS is such a critical thing. So we haven't actually come across a case to date of a complete denial of service by, let's say, the United States, the Russians and so on. So the civil component of these systems have always been free. But that doesn't negate the fact that a denial of service button actually exists. What we have actually had in the past and more recently is repositioning satellites in terms of geometric coverage to give a strong position solution over a given region. So we had that in the Gulf War when we woke up in the UK to find that our receivers were giving us worse positioning accuracy. And then you looked at the way that the satellites were distributed in the sky and you saw that they were much more geometrically strong over the Middle East.
Right. So this was in 1991 this was happening, wasn't it?
Yeah. And then more recently, Russia and Syria. It was obviously using its GLONASS satellites to provide it with better coverage and therefore better positioning accuracy over Syria, because that's how they control missiles and things like that.
So the satellites were repositioned, and then does that mean that people who were using that coverage in another part of the world just don't get the same?
They get degraded performance, because one of the elements of accuracy is geometric configuration. So you want your satellites to be nicely distributed around you, in addition to the satellite quality, the signal quality, to give you a good position, good geometry, good measurement, precision and accuracy, good positioning accuracy and integrity and so on, right? So the way you position satellites around the object that needs to be positioned, the better their performance.
So unless every single nation has its own GPS equivalent, we're never going to get round that particular vulnerability, are we?
Well, it depends. It depends. So, for example, for many years, the UK has worked with the US quite closely because they're very close allies. For example, there could be agreements between countries, between nations, in terms of sharing a facility. So, the Galileo system, which is obviously owned by more than one country, there is obviously an agreement amongst them that it is their system. So, there's something called PRS, Public Regulated Service, which is much more, call it the secure side of things, which is encrypted and so on. So they operate a system as a region, okay? But one of the reasons why most people wanted to have their own is this particular reason, that there is significant advantage to have over the competitor.
Yeah, sure, but it's expensive.
Yeah, with regard to this, but also that the expense of putting a satellite system up, particularly for GPS, has more than been paid for. Because as we can say, it's ubiquitous. And so there are all sorts of revenue streams associated with it. So I don't think the economic case is that, if you do it properly, then it pays for itself many times over.
So one of our recent Zero Pressure episodes was all about building critical national infrastructure resilience.
Yes.
And this is something that really seems to be quite key as part of that. Have there been any examples of PNT systems being targeted or intentionally damaged or disrupted?
Happens all the time, particularly with respect to jamming, spoofing, mickening.
Jamming, spoofing, and what was that other word?
Mickening. So I can explain a little bit what they are. So jamming is where you generate a really powerful signal that overpowers the light bulb, power level signal from GNSS. And that has the potential to wipe it out completely. So then the receiver doesn't receive anything. So that's jamming. Although there are some types of jamming that give you residual signals, which are even lower power. Okay. But essentially it wipes out the GNSS signal. So your receiver is receiving nothing. Right. Spoofing is where you basically broadcast a fake signal. It's a fake signal, right? So the user doesn't really know it's a fake signal because it looks like GNSS and so on. But it gives you hazardously misleading information. Mickening is in between. So what you do is you take the true GNSS signal, you add something to it or subtract something from it, and you rebroadcast it.
Sneaky.
Yeah, very sneaky. So that again leads to hazardously misleading information. And so spoofing particularly could be used by the enemy to bring whatever vessel, whatever object they're interested in to them. So the pirates of the Indian Ocean, some of them were clever enough to be using spoofing to lure shipping lines to them.
God, it's a huge industry, isn't it?
Exactly. So the key really is that the security aspect of this, in addition to those particular vulnerabilities that are more to do with safety and so on, and commercial liability and so on, need to be taken care of. And this is how we came up with the applications that are mission critical. So that could be security critical, liability critical, and so on. And they need protection, including our critical national infrastructure.
We'll go back to Washington shortly. I've also been talking with Juliana Zeus, the research analyst and policy lead on space security, as part of the military sciences team of the UK's leading defence and security think tank, the Royal United Services Institute, RUSI. Juliana, we've heard about national critical infrastructure, but what role is PNT playing in global security and geopolitics?
It's playing a huge role. So PNT services are incredibly important to military operations and are very widely used as part of the general military infrastructure, enabling a lot of the capabilities that we see being used. So especially land forces are almost completely dependent on space for their PNT because GPS is just so integrated in most of their land systems. Why is this important? In a nutshell, we need to know where we are and who we're talking to. So, for example, the prevention of friendly fire incidents is just one big example of this. And if we're looking sort of more into the granular detail of where PNT and specifically Global Navigation Satellite Systems, GNSS, are used in military applications, it goes from the precision navigation for platforms, it's the guidance for smart weapons, it's precision timing that we need for data links and secure communications, and quite simply, it allows for the synchronization of troops. Going from the timing signals all the way to the positioning needs. It's the data transfer capabilities that are sort of secured through space-based PNT.
I'm wondering if there are systems that we would like to be able to be easily integrated, but might not be so if everybody's got their own version.
Yes, that's right. And I think there's a lot to be said about integration into a sort of more international sphere if we're looking at space-based systems especially. And I think this is a big question in particular for smaller space powers like the UK, but also many European powers. I mean, we're looking now at a scenario where NATO has published its space policy and its space strategy. And it says quite clearly NATO will not have its own space-based systems, and it will rely on its member states to supply them. So we're immediately faced with this question of how we're going to integrate and how we're going to be able to cooperate if everyone has their own systems, and how will those systems be able to talk to each other, specifically because we quite quickly hit a sort of classification problem. States have very specific ideas about what is classified material and what isn't. We've seen that before on NATO level, where certain satellite images were not able to be shared, not because the content of those images was controversial or classified, but because the capability with which those photos were taken was classified, so we couldn't share those images. So that's just sort of a small case study in the wider sort of situation, the wider context. So I think integration of satellite systems in general is a big question, and how we're going to cooperate in the future. And I think especially for smaller space powers, that is a huge question, because ultimately cooperation will have to happen.
Thank you very much, Juliana Zeus.
Thank you very much.
And now back to Washington Ochieng. Is there a way round all of these vulnerabilities? I mean, can we not make more use of our ground systems?
Yeah, I mean, it's interesting to say that. In 1997, I think it was, I gave my professorial inaugural lecture.
Oh, congratulations. Always good fun, those lectures.
Yeah, good fun. And my conclusion was that the way forward is a harmonious coexistence between the heavens and the earth. This is the solution to our vulnerabilities problem. So that basically says GNSS plus ground-based.
So what do we do on the ground then? How can we augment stuff on the ground?
So the key really, if you come at it from the vulnerability side, is to be able to understand the vulnerabilities of all systems. Because that's the first thing. If you don't understand the vulnerabilities of space-based and ground-based and so on, then you have no chance of really, augmenting each other. So what we're going to be doing is we're going to be putting together systems that have dissimilar vulnerabilities. There's no point having a ground-based system that suffers from the same vulnerabilities as GNSS. So I think understanding the vulnerabilities of everything before deciding what to put with what is going to be interesting. So really the key to increasing resilience is multi-sensor, multi-system fusion. That's what it has to be. But we've got to make sure that they augment in a synergistic, complementary way.
But I'm thinking when you explained how the satellites worked, that you need 3 or 4 satellites so that you each can actually take a location. You can't do that with 3 or 4 sensors on the ground because they can't see very far, can they?
So it depends. I mean, you can have what we call signals of opportunity. So you can position using Wi-Fi signals or ultra-wideband and things like that. So those will be close to you. So, for example, in this particular room, we will have 4 of them in the room. Obviously, there won't be GNSS here. So we also need to consider the fact that GNSS won't be available everywhere, but where both of them exist, that they can complement one another. So this is what we call seamless positioning, navigation, and timing. So there will be circumstances in your combining of systems where one of them is the master or the de facto and the others are helping. So in the outside, GNSS will be the master with others helping. As you go through the transition, let's say at the door, you have both. some satellites coming through and some measurements from your other sensors. And then you go indoors and you're now completely reliant on non-GNSS sensors. So really it has to be, even in that environment where there is no GNSS, still you have to account for the fact that the systems you're using inside are not vulnerability free. So this is why, we're doing a lot of research in understanding the vulnerabilities of the various possibilities so that we can optimally integrate. But it is a system of systems approach if we're going to do this.
So we could use and have, you talk about indoors.
Yeah.
I'm thinking also, what about underwater? Is that possible?
Yes. Actually, we're working on navigation underwater, including for torpedoes and things like that. And so systems that give you dead reckoning, like sensors, and so on, will work. Systems that use acoustics and so on will work. So there's a plethora of different ways of positioning. Some use acoustics, some use timing and so on, right? So it's really just about making sure that, as I say, we understand the applications, their requirements, and of course, vulnerabilities. The vulnerabilities themselves are not necessarily system level. They are also environmental, as you just put, underwater, indoors, in cities, canyons, and so on.
With all these big buildings that stop the signal.
So really work that is done to understand vulnerabilities is fundamental, obviously, not only to their mitigations, but also ensuring optimal integration. Because suppose you have 25 different things, you're not going to have 25 sensors and systems in your receiver because you don't need that and the computational burden. So there's also the question of optimal integration, optimal combination, what that actually constitutes. So we're doing a lot of work in that area to ensure that it's not just about, numbers, but it's also about the right quantity to integrate, accounting for the trade-offs of things like performance in terms of accuracy and so on, but also computational burden that you end up with and the complexity of it.
So it sounds like we would possibly end up with almost something that's bespoke for a particular, not individual user, but particular type of use.
It's amazing you say that. The example I always give is I'm driving along a freeway where there's no obstruction. I'm happily using GNSS because you can get with multi-constellation 20, 30 satellites at a time, good geometry, everything. You're singing and dancing as you're driving, you're approaching a city. You've got radio broadcasts, you've got your dead reckoning, you've got your, signals of opportunity like Wi-Fi, and I'm acquiring them. And I've got my optimal lookup table in terms of configuration, and I'm absorbing them because my system is open, flexible, almost seamlessly to the user. All I'm getting is the position accuracy, the integrity I want, but the system is sensing the environment and picking what it is picking and integrating in that optimal way, right? So it's not just about the particular use, but the actual systems and sensors themselves may not be the same all the time, depending on where you are. So this is how clever we can make these things. But the key is that the interface to the user is nice, multi-stakeholder type interface. The engine, the user doesn't really care, but the performance delivered. That's the key.
Now, just to finish up, some real quick-fire questions, Washington. Leaving geopolitics aside for now, if you can, futuristically, are we going to need PNT services as we start to travel further out to the moon, to Mars, and, even further? How are we going to navigate, know exactly where we are when we don't have a constellation of satellites or some sensors directly around us?
Yeah, so we do need them now, actually. And they're being used now, so let's say on moon missions and so on. They're basically systems that can be used on the surface. So they're basically using gyroscopes, accelerometers, and others. But yes, I think we will be looking at providing the solar system, where we want to be, where we want to go. There always has to be a way of positioning, navigating and timing. Not just for the purpose of moving from A to B, but also, as we talked about, things like synchronization of comms networks. So, what you might call the solar system grade type comms facilities and so on. They will still need actually PNT, just like we talk about the critical infrastructure here. So yes, we do. And so wherever the human wants to go, whether as human missions or non-human missions, we'll have to have it. As simple as that.
What can nations do to ensure that PNT is used for good rather than for bad things?
Yeah, I think collaboration. And I think the European model is a very good one. Where 27 countries now, I think, are actually working together to develop Galileo as a system. If you look at the civil sector in terms of the underpinning that PNT gives it, so whether that's social, whether that's economic, whether that is environmental, it is a true utility for even contributing quite significantly to saving the planet from a climate change perspective. For example,
that's a big one.
For example, we've shown at Imperial College, for example, that the altitude at which an aircraft flies has got a very, very strong correlation to its contribution to contrail formation, which is obviously a greenhouse gas problem, right? So whichever pillar of society, social, economic, environmental, what you will find is that PNT, either direct or indirectly, is a force for good and a force for saving the planet. And if countries can collaborate to utilize this facility, particularly from those pillars of social, environmental, and economic, then the world can be a much better place.
Washington, thank you for a thought-provoking insight into the world and space of positioning, navigation, and timing.
Very welcome, Helen. And thank you very much for having me today. I've thoroughly enjoyed our chat today.
It's been great. Thank you. So Washington was talking about the future of PNT for navigating difficult environments like underwater, urban environments, and even inside buildings. How one system can support both civilian and military applications, and the role ground-based systems can play in improving the resilience of space-based PNT services, with one augmenting the other in a system of systems. Thank you for joining us on this podcast discussion. In the next episode, we'll be exploring the promising new opportunities and applications the 5G and future Gs networks can bring. What will increased data processing and speed and lower latency in the networks mean for our society? And will it have military implications? In the meantime, I'll leave you with this thought from the astronaut Buzz Aldrin. Timing has always been a key element in my life. I've been blessed to have been in the right place at the right time.